Okay, then we move on with the next talk, which is by Sungwoo Lim on microtextures and strengths of microwave heated lunar simulant JSC-1A. And I'm afraid you will have to read that title again. So take it away. Just JSC.
Sure. Yeah. Can you see my screen?
Yes. Can you go into full screen mode? Yeah. Yes, that's perfect.
Okay. Okay. Right. Thank you. Thanks for James's explanation about our microwave stuff. So today I'm going to talk about the actual microwave heating experiment on behalf of our colleagues at the Open University and the European Astronaut Center. So James already showed these pictures, and I'm sure quite a number of you have seen these pictures already because I've been talking about this stuff for a couple of years. So basically, at the Open University, we're trying to develop an extraterrestrial construction process and resource extraction method utilizing a 3D printing technique and also a microwave heating method. And that's why we designed and commissioned this equipment. And back in 2019 and 20, we started to do a microwave heating of a lunar simulant experiment. And at that time, we've done that under the atmospheric condition, and we used one material, which is the JSC-1A, Lunar Mare regular simulant. And we tested the 5 input powers, starting from 250 watt to 1000 watt. But we kept the total energy input as to 900 kilojoule. What this means is a sample with a 250 watt input power was heated for 60 minutes, while the sample with a 1000 watt input power was heated for 15 minutes. Then we starting to analyze the microtextures, mechanical properties, and the densities of the heated samples. These are a couple of examples. I show you here 1000 watt, 600 watt, and 250 watt of heated sample. Excuse me. And what we found through this experiment was the input power directly affected the mechanical properties and the density. So in general, a higher input power allows higher mechanical properties and density. And you might think about that that's quite pretty common. But anyway, that's what we found. And when you saw these BSE images, you see the number of white dots. Those are the ion-rich spinel-like particles. And these are mainly like hematite or magnetite, which you can find from the iron ore on the Earth's environment. So, and each input power also shows the quite unique features for the mineral crystallization features here as well. So, excuse me. What we summarized our finding was if we use lower input power, it could be beneficial to extract the iron. And while if we use higher input power, it could be useful to fabricate materials for construction purpose. So we summarized our outcomes and published that to the Nature Scientific Reporter last year. Then we moved to the next stage. Because our previous work was all done under atmospheric conditions, now we had to do the same thing under the vacuum condition. So we tweaked our system, attached the vacuum pump, and starting to do the same experiment. But this time, we used more materials, including JSC-1A and OPRH3N, which is a lunar highland regular simulant developed by Off-Planet Research. Excuse me. And this time, we only use 3 input powers, 1000, 600, and 250 watt. The reason why omitted the 800 and 400 watt is because those input powers does not show much distinctive features, I mean, the mineral crystallization features compared with the other input powers. So we reduced the candidate as 3 input powers. Then we started to experiment. At the moment, we are currently almost finalizing our experiment and analysis. And during this experiment, we have faced a couple of challenges. The first one is strong plasma effect. If you do the microwave heating experiment under the 10-8 millibar or lower, you wouldn't actually see any plasma effect. So when you do the the actual microwave heating on the lunar surface, we don't have to worry about it. But here we are in our system, because of the limitation of the pump is capable to reduce the pressure up to 10 minus 8 millibar, which is really marginal. And then the material has a lot of dust. It introduces the dust environment, and also there are some moistures introduced inside of the microwave system that actually affected lower the material capability. So we end up with experiment around 10 minus 4 to 10 minus 5 millibar only. And this high pressure, I mean, compared with the 10 minus 8 or real lunar surface, like 10 minus 50 millibar, with this high pressure, the samples are actually experiencing a high plasma effect. And this plasma effect actually disturbs the microwave energy absorption, and leading to the poor heating performance. The other challenge was, because of the low pressure, the volatile extraction was really extreme. So as you can see from these photographs, the melted samples formed as like a sponge-like creature. So when you see the microtexture, you see lots of abundant bubbles inside of the structure. And that was also caused a bit of a problem. So in general, again, the input power also directly affect the mechanical properties and density. So for the mechanical properties, higher input power allows a higher mechanical properties, just like the samples on the atmospheric condition. But for the density, the story is completely different. If you see the number of density, actually this is not the final number, it's just a ratio, because we are currently continuously updating the experimental result. So I only displayed the numbers as a ratio. If you see the 1,000 watt of sample density, which is 1, and the 600 watt and 250 watt density, you will see the higher input power actually allows a lower density. And this is because of the abundant bubbles. So we crushed the 1,000 watt samples and measured the density again. This is true density, not bulk density. Then we can see that the density is much increased, but still it's quite behind of the other input powers. We are expecting like a linear relation, but the 1,000 watt has a much lower density. One of the reasons we might think is that there might be still lots of micro bubbles inside of this sample structure. Maybe that affected this measuring the true density. And the mineral crystallization features are all also depending on the input power, quite similar to the samples done on the atmospheric conditions. Highland sample is somewhat different. As James mentioned before, we realized the Highland Simulant or Regulus has a much lower heating performance. This is due to the its dielectric properties that actually determine the microwave absorption rate. So this is a mechanical material properties of the Regulus. So what we can improve is only we can try to find the resonant frequency for the specific materials to mitigate this stuff. But anyway, for now, as you can see, the Highland Simulant, Highland material requires a higher input power with a longer heating time. So in this case, we only use 1,000 watt with a 60 minutes heating time, which is 4 times longer than the modern Regulus. And when you see the structure, it's still only sintered. It doesn't show any partially molten or fully molten area. Anyway, these are current our findings, and we are continuously analyzing our current observation, and hopefully we can publish some interesting outputs very soon. And so whatever the other problem is, whatever we've done and we are currently doing is everything is a simulation. The experiment environment is simulated and the material is simulant. But that's why I'm always saying we need to do these types of experiment on the lunar surface using real lunar Regulus and trying to get the more accurate data. And this is why the Open University is teamed up with Added Value Solutions UK Ltd and the VIFA-RF. So we are currently developing a microwave heating demonstrator payload. So thanks to the UK Space Agency and the European Space Agency, we were able to secure 4 consecutive contracts from them, and we are continuously improve our payload design. The current payload budget requires only 450 watts of input power, which is dramatically reduced from our original payload design, what was about 800 watts. And the total mass of the payload is now 10.84 kilograms, again reduced from 12 kilograms, even including the excuse me, the methane CH4 and the H2 tank, because now we're adding the oxygen extraction function as well in our payload. Anyway, as part of this payload development, we are also doing some interesting computational simulation as well. So in this simulation, we use 2 different materials, Lunar, Mare, and Highland regolith, with 2 different starting temperatures, 80 and 400 Kelvin. The reason why we use different materials with a different starting temperature is because we want to make sure our payload works anywhere on the lunar surface. So that includes the permanently shadowed area under the crater rim, whether the temperature goes as low as 8 Kelvin, or on the lunar surface anywhere directly exposed by lunar daylight with the temperature up to 400 Kelvin. So through this simulation, yes, we can, thank you, we can claim, so we can see that our cavity design and nicely hit the entire sample and even completely melting the core of the sample. But our original plan was we are trying to melting the entire sample, which is not the case in this simulation. So one of the reasons is the electric field inside the sample is fluctuating with the temperature increase, as you can see from this curve. So when the sample is heated, the electric field is dramatically decreased, and then spikes with the thermal runaway, and then decrease again to the certain level. And this leads to the poor heating performance at the later stage of the microwave heating. But this phenomenon is because of the material properties of lunar regolith. So we are trying to find the mitigation way to optimize and maximize our heating performance of the cavity design. So in general, Open University and our team is trying to support the ESA's space exploration roadmap. So we are aligned our development roadmap to the ESA roadmap. And I believe some of you are lunar scientists. So if you have any interesting experiment you want to do on the lunar surface that's related to the heating lunar regolith, please do contact us so we can discuss to add your experiment to our payload. With this way, we think we can increase the chance to be selected as one of the technology demonstration payloads for the ESA's ELS missions. So thank you for listening. Now I would welcome your questions.
Thank you very much. Great talk.